Section: Introduction. In this section, we discuss the evolution of blockchain technology, which initially gained attention through Bitcoin, a decentralized cryptocurrency that functions without a central authority. The introduction of smart contracts expanded blockchain's use beyond digital currencies into areas like finance and supply chains. Smart contracts are self-executing programs on the blockchain that enable trustless interactions. Ethereum, a leading platform for smart contracts, sees about 70% of its network traffic from these transactions. However, Ethereum's method of executing transactions sequentially creates a significant performance issue, limiting its capacity to around 30 transactions per second. Additionally, its reliance on a resource-heavy proof-of-work consensus mechanism further restricts scalability. As blockchain use increases, it is essential to address these execution and consensus challenges to enhance performance. Recent advancements in consensus protocols have shifted the focus from consensus issues to the execution of smart contracts. Newer protocols like Conflux and OHIE can handle over 5,000 transactions per second for simple payments, but execution remains a challenge, especially since smart contracts require sequential processing to maintain state consistency. One way to improve throughput is to pack more transactions into each block without changing the block generation rate. However, this can increase execution delays when transactions are processed one after another. Using multi-core processors for parallel execution could help, but determining which transactions can run in parallel is complex, particularly with smart contracts. We need to ensure that parallel execution produces the same results as sequential execution, which requires careful scheduling to avoid conflicts when transactions access the same state. A practical method is to run non-conflicting transactions in parallel while keeping conflicting ones in a serial order, balancing performance with correctness. Various frameworks have been proposed to enhance transaction throughput, but some require explicit annotations for read-write sets, making them impractical for general smart contracts. Others use static analysis to identify dependencies, but this often leads to overly cautious scheduling, missing opportunities for parallel execution. Some solutions use optimistic concurrency control, allowing transactions to run in parallel without tracking dependencies, but this can lead to performance issues due to frequent aborts and retries, especially in high-contention scenarios. Even when parallel execution is effectively managed, the benefits can be limited by storage layer bottlenecks. Research shows that disk I/O accounts for about 70% of execution overhead due to I/O amplification, where small state changes require multiple disk accesses. In Ethereum's traditional model, reading state involves navigating the Merkle-Patricia tree, which adds latency. After execution, state updates must also be saved back to storage, often needing additional sequential operations. Since all parallel execution models share the same state database, storage access remains a critical limiting factor. As blockchain systems grow to handle millions of accounts and contracts, improving storage efficiency is vital for realizing the full potential of parallel execution. In this paper, we introduce Reddio, a batch-based parallel transaction execution framework that effectively tackles both computational and storage bottlenecks in modern blockchain systems. Unlike previous methods that focus mainly on transaction scheduling while keeping storage operations sequential, Reddio optimizes execution across both transaction processing and state storage layers, significantly boosting throughput, scalability, and overall efficiency. Reddio uses a batch-based execution model, grouping transactions into batches for parallel execution. This approach allows for better scheduling of independent transactions, reducing state conflicts and synchronization overhead compared to executing transactions one at a time. However, simply parallelizing transaction execution is not enough if storage operations remain a bottleneck. To solve this, Reddio introduces an asynchronous state database that separates execution from storage tasks, enabling efficient processing of storage updates without hindering transaction execution. To achieve high performance, Reddio incorporates three key techniques in the storage layer. First, it allows direct state reading from a key value database instead of traversing the Merkle-Patricia tree for each access, which cuts down read latency and minimizes I/O amplification. Second, It retrieves necessary tree nodes asynchronously while executing transactions, ensuring that storage access does not slow down performance. Lastly, Reddio employs a pipelined workflow where transaction execution, state retrieval, and storage updates occur in overlapping phases, eliminating serialization bottlenecks and maximizing hardware parallelism. By combining batch-based execution with an asynchronous state database, Reddio effectively enhances parallel execution efficiency while addressing the storage limitations that typically impede blockchain performance. Section Summary. In this section, we discuss the limitations of current blockchain systems, particularly Ethereum, which faces performance bottlenecks due to sequential transaction execution and storage inefficiencies. We introduce Reddio, a batch-based parallel transaction execution framework that optimizes both computational and storage layers, enhancing throughput and scalability by decoupling execution from storage operations and employing techniques like direct state reading and asynchronous node retrieval. Section Main. In this section, we outline the organization of our paper. We begin with background information that highlights the necessity for parallel transaction execution in blockchain systems. Next, we provide an overview of Reddio's workflow and its key design principles. We then detail Reddio's architecture and present a formal proof of its correctness. Following that, we analyze the system's performance, including its correctness guarantees and recovery mechanisms. Finally, we conclude by summarizing our contributions and discussing future research directions. In the background and motivation section, we introduce essential concepts for understanding the rest of the paper. We follow Ethereum's account model, which consists of two account types, user accounts and contract accounts, each identified by unique 160-bit addresses. User accounts hold Ether and can initiate transactions but do not contain executable code. In contrast, contract accounts have executable code and maintain a storage area known as the contract state, which consists of key value pairs mapping 256-bit words to other 256-bit words. The combined storage of all accounts forms the blockchain state, managed by a state database. Users interact with smart contracts by sending transactions to invoke their functions. When a function is executed, its current state is retrieved, updated, and then stored back. Ether transactions allow direct transfers between accounts without executing the Ethereum Virtual Machine, EVM. In a typical blockchain system, full nodes synchronize and execute all transactions within blocks, updating the ledger state, which consists of key value pairs. Each block header includes a cryptographic hash of the updated ledger state, allowing light nodes to verify its correctness. Additionally, state storage requires tracking data history for transaction auditing, often implemented using Merkle trees, like the Merkle-Patricia tree used in Ethereum. Regarding the workflow, at each block height, the state database operates in three phases: update, hash, and store. During the update phase, the EVM reads and writes state values for transaction execution. After processing all transactions, the state database recalculates the new root hash by recomputing hashes for modified nodes. Finally, in the store phase, these modified nodes are saved to an underlying key value database, such as LevelDB in Ethereum. Currently, these phases are executed sequentially for each block. For smart contract parallel execution, once a block containing a series of transactions is added, nodes execute these transactions in the specified order to update the blockchain state. This serial approach ensures consistency across nodes but significantly limits throughput. A potential solution is to utilize multiple cores to execute transactions in parallel, a concept well studied in databases. These protocols typically ensure that the outcome of concurrent execution is equivalent to a serial execution in some order. However, this order may differ across executions, leading to inconsistent states among nodes. Parallel executions in blockchain must also meet deterministic serializability criteria, ensuring all nodes achieve the same result for every block. A schedule for a batch of transactions is deterministically serializable if its effect matches that of a serialized execution that follows the transaction's commitment order. Recent works have explored parallel transaction execution for smart contracts. Some assume that accurate read-write sets are readily available, which presents practical challenges, as seen in Fisco BCOS, where users must specify these sets. Others use optimistic concurrency control, OCC, to execute transactions in parallel without needing read-write sets. With OCC, transactions read from a state snapshot, allowing parallel execution. However, validators must abort and re-execute transactions that violate deterministic serializability. Unfortunately, existing approaches have not achieved linear speed-up on real-world Ethereum workloads due to limited inherent parallelism, as frequently accessed shared variables often force sequential execution. These methods apply coarse-grained transaction-level concurrency controls without considering smart contract logic, missing opportunities for parallelism by analyzing state access patterns at a more granular level. In this paper, we aim to develop an alternative approach that adapts to the existing Ethereum architecture to enhance parallelism by minimizing transaction conflicts. Section Summary. In this section, we describe Reddio's account model, which includes user and contract accounts, and explain how transactions interact with smart contracts and the state database. We also highlight the limitations of current serial transaction execution in blockchain systems and propose an alternative approach to enhance parallel execution by reducing transaction conflicts, aiming for improved performance while maintaining deterministic serializability. Section: Motivation. In this section, we discuss the motivation behind our work. Ethereum uses a sequential model for processing transactions, meaning that transactions in each block are executed in a specific order to ensure consistent results across the network. However, this method limits efficiency because even transactions that do not affect each other must be processed one after the other. As the number of transactions increases, this sequential approach becomes a significant bottleneck, slowing down the system and increasing the time it takes to confirm transactions. While improvements in consensus mechanisms have helped reduce delays in block propagation and finalization, the way transactions are executed has become the main performance issue in modern blockchain systems. If we do not optimize transaction execution, we cannot fully benefit from faster consensus, which limits the scalability of the blockchain. Additionally, Ethereum state management adds to these performance issues. The state database, which uses a structure called the Merkle-Patricia tree, MPT, creates a lot of computational and input-output overhead due to frequent cryptographic operations. Research shows that operations related to the MPT account for about 70% of the overhead in transaction execution, as each transaction requires multiple lookups and updates in the tree, leading to heavy disk and memory usage. Moreover, the synchronous nature of the state database limits the advantages of other optimizations. Even if we parallelize transaction execution, the need for sequential state updates remains a bottleneck, preventing us from fully realizing the benefits of parallel execution. To overcome these challenges, we need to optimize both transaction execution and state management to improve blockchain scalability. A parallel execution framework that efficiently manages independent transactions while reducing state access bottlenecks can significantly boost blockchain performance, allowing for higher throughput and lower latency without sacrificing consensus reliability. Next, we provide an overview of Reddio's approach to parallel execution and storage optimization. We recognize that while parallel execution can increase transaction throughput, its advantages decrease as the number of execution threads rises. After a certain point, input-output overhead becomes the main limitation. As we noted earlier, read and write operations to the state database contribute significantly to execution overhead due to the MPT structure. Therefore, simply relying on parallel execution without optimizing the storage system will not fully harness the potential of parallelism. To tackle this issue, we enhance the state database by implementing direct state reading, asynchronous node retrieval, and a pipelined workflow. Currently, when a state value is requested, the system must find the root hash of the tree and navigate through it to get the value, which involves loading many nodes and results in multiple rounds of input-output amplification. Since these structures mainly ensure state integrity rather than provide direct execution semantics, we allow the Ethereum Virtual Machine, EVM, to access state values directly, skipping the need to retrieve intermediate nodes. When a state is updated, all nodes along the path must be loaded for hash recomputation. To reduce input-output blocking, we store the new state value in memory and load the necessary nodes asynchronously. However, even with these improvements, the asynchronous workflow still has performance limits. Specifically, the phases of hashing and storing must occur in sequence after the update phase, which is tied to transaction execution. This sequential dependency prevents throughput from scaling linearly with the number of execution threads, creating another bottleneck. To resolve this, we adopt a pipelined workflow. After executing each batch of transactions, we selectively rehash and save certain nodes in the account and storage tries to the underlying key value database, creating a pipeline between execution and state persistence. However, if we hash frequently modified nodes too early, it could lead to unnecessary computations and storage use. To avoid this, we dynamically find the best point for early hashing, ensuring recalculations are infrequent while maintaining storage efficiency. This pipeline design allows us to use resources better and sustain high transaction throughput. We also implement a batch-based optimistic parallel execution scheme, where each transaction runs independently on a copy of the global state database without any communication between threads. At the start of each batch, we select a set of transactions for execution in the next round. Once we have the batch of transactions, we schedule their parallel execution. Each transaction is assigned to a worker thread, which starts an EVM instance for execution. Each thread runs its assigned transaction in parallel on a separate copy of the state database. This method ensures that transactions operate independently on different threads without direct interactions. During execution, each thread keeps track of the data it reads and writes. Although we carefully select the batch to avoid explicit conflicts, implicit conflicts can still occur, such as when multiple transactions call the same smart contract, leading to unintended dependencies. If a transaction reads data that has been updated by a previous transaction, we abort it and return it for future execution. If there are no conflicts, the transaction is committed, and we merge its updates into the new state database. Finally, we return the updated state database and the write set. Section Summary. In this section, we address the performance limitations of Ethereum's sequential transaction execution and state management by introducing Reddio's parallel execution framework, which optimizes transaction throughput through direct state access and an asynchronous, pipelined workflow. Our approach allows independent transactions to execute concurrently while efficiently managing state updates, ultimately enhancing blockchain scalability and reducing latency. Section: Asynchronous State Database. In this section, we discuss the asynchronous state database. While running tasks in parallel enhances computation, accessing storage remains a significant challenge due to its sequential nature. In Reddio, each worker thread uses a lightweight copy of the state database, but they all rely on the same key value store, which creates sequential read dependencies among threads. As the state database grows to millions of accounts, storage latency becomes the main bottleneck, limiting our speed improvements. To address input-output bottlenecks, we implement an asynchronous workflow that separates execution from storage. However, this introduces challenges like accessing outdated data and unpredictable write bursts that can overload the storage system. To tackle these issues, we carefully schedule state commits to balance execution efficiency with storage consistency. We introduce three main optimizations: direct state reading, asynchronous node retrieval, and a pipelined workflow, which we will detail later. These strategies help reduce the delays caused by sequential state access, enhancing our execution efficiency and overall system performance. Regarding the account tree, when we rehash a storage tree, we also update its corresponding leaf node in the account tree, prompting us to rehash the account tree at the node level. For each node, we estimate a commit point, after which we expect the node to remain unchanged, allowing us to rehash early. We use different asynchronous processing strategies for storage tries and account tries based on their access patterns. storage tries are processed at the account level due to lower contention and predictable access patterns. If we anticipate that a contract account won't be accessed again within the block, we can rehash its storage tree speculatively. In contrast, the account tree is frequently accessed and modified by multiple transactions. To minimize redundant computations from these concurrent modifications, we use a more detailed asynchronous pipeline for the account tree, determining a commit point for each node individually. We delay rehashing until a node is unlikely to be modified again, which improves efficiency while ensuring consistency. After each batch execution, we check if a contract account will be accessed by any remaining transactions. If not, we speculatively rehash and save the storage into the node database. Although there could be rare cases where an internal transaction might access the account, we consider this an acceptable risk. We also employ 2 additional threads to manage the hashing and storage phases in parallel, while the commit thread triggers the update phase. Ideally, when a node completes one phase, it moves immediately to the next, allowing for concurrent processing. However, nodes closer to the root may be modified multiple times, delaying their commitment to the hash phase. To address this, we estimate a commit point for each node, indicating when further modifications are unlikely. Once this point is reached, we commit the node for hashing. At the end of each batch execution, we call the asyn commit account function, which queues all nodes that have reached their commit points for hashing. The hash thread continuously processes these nodes, recalculating their hashes and attempting to hash their parent nodes once all child nodes are done. The hashed nodes are then queued for the storage phase, where the store thread serializes and writes them into the node database. In our asynchronous workflow, nodes are accessed simultaneously during the update, hash, and store phases. To prevent issues when a node is being hashed while being modified, we assign a lock to each node for exclusive access during processing. Before a thread hashes or stores a node, it checks for any modifications since the last update. If changes have occurred, the process is aborted to avoid using outdated data. For simplicity, we do not explicitly detail this mechanism in the algorithm. Section Summary. In this section, we describe how Reddio addresses storage access bottlenecks in its asynchronous state database by decoupling execution from storage and implementing optimizations like direct state reading and pipelined workflows. We also detail our strategies for managing the account tree, including estimating commit points for nodes to improve efficiency while ensuring data consistency during concurrent modifications. Section Framework. In this section, we present the overall framework for Reddio's parallel execution of the Ethereum Virtual Machine, EVM, with asynchronous storage. The main thread, which we refer to as the coordinator, manages the process. Initially, we set up the necessary threads, including retrieval threads for nodes, a hash thread, and a store thread. The AC commit storage thread is tasked with committing the storage tries of smart contracts. We then enter a main loop that processes transactions in batches until all have been handled. In each iteration, the coordinator retrieves a batch of transactions, assigns worker threads for concurrent execution, and gathers the resulting updates. For each account recorded in these updates, if it won't be accessed explicitly, we flush all updates to that account's storage tree for asynchronous commitment. The commit threads continuously take accounts from the commit queue and apply updates to the storage tries. Next, the coordinator triggers the pipelined workflow for the account tree and waits for all threads to finish the commit process before returning the updated state database. To ensure the correctness of Reddio's protocol, we demonstrate that it meets the criteria for deterministic serializability. Essentially, if a transaction reads a stale value, it will be aborted, and the incorrect results will be reverted. We prove that if a transaction reads a stale state value, it will eventually be aborted and re-executed in future batches. We also show that the results from Reddio's parallel execution match those from serial execution. By using induction, we establish that if earlier transactions do not read any writes from later transactions, the parallel executions maintain deterministic serializability. Regarding commit point determination, we discuss how to identify the commit point for each node in the account tree. We assume that the first 4 levels of the tree are fully populated and estimate the commit point for a node as the point where no further transactions will modify it. Although predicting this point exactly is challenging, we estimate it based on the number of remaining transactions and their expected updates. For nodes at deeper levels, we set a commit point based on the total number of transactions in the block. If a node is a leaf in the account tree and its associated account is still being accessed by remaining transactions, we cannot hash it, even if it has reached its commit point, since it will need to be modified again when the account is updated. Section Summary. In this section, we present Reddio's framework for parallel EVM execution with asynchronous storage, where a coordinator manages threads to process transactions in batches, ensuring updates are committed asynchronously. We also discuss the method for determining commit points in the account tree, estimating when nodes can be safely hashed based on the likelihood of further modifications from remaining transactions. Section: Recovery. In this section, we discuss recovery. To facilitate direct state reading, we record state values in the database during the store phase of each state update. However, if a machine node crashes, only some of the state updates might be saved, which can lead to inconsistencies. When the machine node comes back online, it needs to replay the blocks to restore the correct state. During this process, we might read inconsistent state values, which can affect correctness. To solve this problem, we enhance the record format to include the block height where the state update happened. When we replay from a specific block, we discard all state values that have a height greater than that block. This way, we ensure that we retrieve the correct state values, keeping everything consistent across updates. By adding block height information, we make sure that state values stay consistent after recovery, preventing issues from incomplete writes. This method also allows us to restore the state efficiently without needing to fully resynchronize the database.